Okay, we're going to be trying out the Cavendish experiment here. I've been letting the torsion balance come to rest over the course of about 24 hours now. Even with that amount of time, I think just from the air circulation from the heating and cooling system, I've still seen a small amount of motion here. So in the last about 10 minutes, I've seen this end move from here over to here. So that's probably about 10 degrees in 10 minutes. I'm going to let this, I'm going to just gently touch this and try and bring it to rest and observe for another couple minutes. And then whichever direction I see it moving, I'm going to put the bowling balls that are my other masses on the opposite side as that, just so we can verify that there actually is a change in direction, a change in the direction of the acceleration of these things as they rotate. I don't think we're going to be able to get it to a position where they're totally stopped initially. So this seems like the best way that we can still verify that there is some force from gravity between the masses I have on the ends of this meter stick and the bowling balls that I'm going to put in place. So very gently, I'm going to be just trying to stop any motion that we have in there, just a tiny, tiny force. I'll mark where it is right now. Whichever direction I see it move in. After this, I'm going to put the bowling balls on the other side. No, actually, I'm going to try this again. I think I gave it a little bit too much force, even with just that very gentle touch. I see it already moving quite a bit. Let's check that one more time. Looks like that's moving just very slightly, if at all, right now. I can't see any motion. So we'll let that go for a minute, see which direction it's moving, and then put the bowling balls on the opposite side. It looks like in the time that we've let it go, it's moved from here over this way, so it's rotating counterclockwise when viewed from above. So I'm going to put the bowling balls in place on this side and that side over there, try and pull it back clockwise, and we'll see if we can get some noticeable acceleration in that direction. So it looks like we've had our first contact between the masses at the end of the ruler, the meter stick, and the bowling balls. So that's pretty exciting. We did see that motion toward the bowling balls then. Now there is still the question of where that equilibrium position was for the string. It didn't occur to me until just now, but when I marked the spot that it had started at and noticed that it had rotated this way, that could have been an effect of the velocity that I gave it initially. It may not have been accelerating that way. Maybe it would have rotated back this way on its own. So for that, we'll have to go to the video and see if we can observe some acceleration in this direction, or whether that was just my initial velocity. But right now, it looks like a successful test and a successful replication of the Cavendish experiment. After viewing the video, I'm really happy with the results. When I went back and looked at this, after I last touched the torsion balance, this end was moving this direction, so it was rotating clockwise. But on its own, it came to a stop and started rotating back this direction. So we must be really close to the equilibrium position on this right now. So when we started it, it was over this way, to this side of the equilibrium position, and still moving this direction. When we put the bowling balls on there, it turned around, which it would have done anyway to get back to its equilibrium position, but it went way beyond where it had gone the first time. So regardless of which direction it was moving when I put the bowling balls in there, we can see there was some clear effect of the force of gravity from those bowling balls, pulling it much, much farther than it would have gone just due to its own oscillations. So again, this is a really nice example of the force from gravity between two very small objects. Good replication of the Cavendish experiment. Hey folks, how you doing? We're looking for a replication on the Cavendish experiment here. So we've got our torsional balance with just a piece of wire suspending this metal rod here with two weights on either side. And I've been letting this come to rest over a long period of time and doing just really fine adjustments, trying to get it perfectly still. We're then going to add weights, or add bowling balls for masses near the two ends of the rod, and try and get that gravitational pull to cause this whole thing to twist. So first thing we need to do is establish our baseline. What kind of motion are we seeing with this thing without the interaction of the bowling balls on this? I've been letting this thing calm down all day, and it still isn't perfectly still, but it's really, really close. So I'm just going to watch for a little bit, and you guys get the benefit of high speed. I'm going to be sitting here bored as heck as I watch as this little laser goes back and forth. So we've got a laser here bouncing off a mirror on the rod and then falling onto the ground right here. So you can sort of see that in the video, it looks like. Yep, I think we're okay. And that's just going back and forth a little bit. I've got the meter stick to provide a point of reference so we can see the motion of this without the bowling balls. And then we'll put them in place and see if we can observe some noticeable changes. Hopefully, keep your fingers crossed. All right, so let's see how this thing goes. And get a clock in the picture too, so you can see just how dedicated I am, how much time I'm sitting here watching this little laser go back and forth a few times. I'm going to put some marks on the floor so we have a baseline mark so we can see any differences there. Well, it looks like we're not quite as steady as I was hoping. We still are seeing some shifting, so it's oscillating back and forth, but it's changing the range over which it's oscillating right now. So I think I better let this one sit for a little while and come back to it first thing tomorrow morning after it's had the whole night to settle down. Hopefully it doesn't get bumped between now and then, and we'll see if we can get some more at that point. Cross your fingers for me. Hey folks, we're back. It's the next day, and I've got this thing pretty stable, or at least it has been. I've been literally tiptoeing around the room to try and avoid moving air as much as possible. So we are looking for such a small amount of force with this. It just has to be so sensitive that even little tiny disturbances can disrupt it. I put a little paper down to make the mark easier to see, and it's graph paper, which makes it easier for me to tell when it's moving and when it's not. So I'll give you the benefit of the high speed here as I mark the current motion of the laser light here as it goes back and forth. And then once we kind of get an idea for the range of motion, hopefully fairly small range of motion, we'll put the bowling balls in place and see how that range changes over time. Boy, I'll tell you, one thing that is really frustrating about this experiment is just how sensitive this equipment is. Right before I started the video, I watched this thing go back and forth 4 times, and it was going over about a distance like this. I didn't do anything except walk over to the computer to turn on the recorder, and now we have at least twice as much oscillation here. So, boy, there's a heck of a lot of variance here. But hopefully, we have sort of a consistent middle point in here, and we can watch how that middle point in the oscillation changes over time. Back to the high speed for your benefit. I'm going to sit here in real time. Okay, well, let's call it there. So we do see some swinging back and forth and some variation in how far this thing is swinging, but it looks like we're keeping a center that's right around this area. So even though we have oscillation around that point is pretty consistent. A little bit of uncertainty on that, but we're not going to require too much certainty on that number, hopefully, to begin with. So next step, I'm going to tiptoe super carefully, super slowly over to get the bowling balls and place them next to our apparatus, and then we're just going to let it run for a while and see what our new center of oscillation is. I'm going to put the bowling balls so that it should cause this bar to twist in this direction, which means we should shift our center from here over in this direction somewhere. So hopefully, I can manage to walk 10 feet and place 2 bowling balls without causing much uncertainty in these results. But we'll just have to see. It appears that we're actually exceeding our previous range. We're very close to it right now, and this is a very sensitive system. Well, let's see what we can do. I think my best course of action here is just to remove myself from the situation entirely and see if we can get this thing to oscillate on its own without interference from me. It looks like I've already caused a little disturbance in this, and maybe the fact that we're seeing this get so far over to the right, that may actually be more of a result of me just moving nearby this thing than those 2 bowling balls in place. So we'll have to watch what happens over time with this. I'm just going to let this run. You guys get the high speed. Well, it's been about 10 or 12 minutes of me sitting quietly in the corner trying not to screw anything up, so let's see where we're at with this. I'll give you guys the benefit of the high speed again, and I'll make a few more markings. We'll see where our new center is and how it compares to the old center. Well, clearly my interactions have caused a bigger swing back and forth, but it also looks like our center has shifted. So we'll make some measurements in just a minute to verify that, but it looks like we have caused some kind of a shift as a result of including those bowling balls. So let's wait to make the final conclusion until we've seen a few more swings back and forth, get a few more trials worth of data on here. But I think we're looking good here. We may actually have one that worked out. got our data set. Let's analyze it next, but first I'm going to stop this video and save it because holy cow am I going to be sad if something happens to corrupt this file. Let's do that now. Alright, well I think everything's saved okay, so we should be in the clear. I want to make some actual measurements on this so we can kind of get some numerical estimates of how much the orientation of this thing shifted over time. So I figured maybe a good way to do that was by measuring angles rather than measuring distances, or at least trying to get things kind of relative to some consistent arc. So I wasn't super careful when I made the marks about starting my mark at the same spot where the laser started, which I should have been. But I did kind of draw on top of the laser, so I'm just going to put a piece of string down, tape it right underneath the very center point of that torsional balance, and then make an arc, and then we can kind of mark from there and make some measurements of center point and how that shifted over time. So let's get that that all marked up, and then we'll see where we're at, how much of a change we actually observed on this. But so far, looks really good. Looks like we actually did observe a change on this, so score. Thank goodness we already made the measurements. My tie brushed against this, and look how much it changed already. So sensitive. Oh my gosh. Alright, let's finish this thing up. So I've got I extended the paper a little bit while it was still on the floor. And I have the very bottom of the paper, or the very edge of the paper marked right here. That's where the center of that, where the kind of the pivot of that lever was. So all of these marks, then I'm going to measure an angle relative to this protractor that I have taped in place, and then we'll kind of figure out where the middle of that angle range is. So what angle was that thing pivoting around? And what we should be able to see then is that we have, a different average angle here than we do here, or, noticeably different for all 4 trials than for these 4 trials. So let's just go ahead and measure these, and we'll see how it comes out. Trial 1, let's see, purple. Okay, trial 1, it looks like we went from an angle here in purple that was 104 degrees. To here, which is 89 degrees, so 89 and 114, average between those two would be, let's say 107.5, call it 108. Whoops, realized I screwed up on my first measurement, so let's go back, try that one more time. So here, I called that one 114 before, but actually that's 104 degrees, not 114. And then this one is, actually that looks like it's right about at 90 degrees. So 104, 90 degrees, the average between those would be 97 degrees, not 108. Okay, and we'll just kind of go through the rest of this in the same fashion, so I won't make you wait through my calculations. I'll give you the high speed again. Okay, so we end up with pretty consistent results for these 4. Those were before the 2 bowling balls were put in place. So almost all right at 96.5, just that one that was off by half a degree. So really nice consistency on that. Let's see what we get for the other 4 trials. All right, so we get, a noticeable difference here. We get about 96.6 degrees there for an average, and on this one we're just shy of 95, so maybe 95.8 degrees. So, not a huge difference, but maybe a degree off. Now, we are looking at extremely small forces, and so even though this is a very sensitive instrument, we wouldn't expect to see huge changes. Now, just as far as what this looks like, and as far as the angle shift, let's take a look at what that would look like, where the centers for each one of these things would lie. So I'll just do 2 different colored lines here. One at 96.5 degrees, as close as I can manage. And then the 95, just shy of 95 degrees on this one. And we end up with just this little tiny pivot, but definitely a noticeable, when we're careful enough, a noticeable shift as a result of the gravitational force, not from the Earth, not from the moon or the sun, but from two bowling balls. Cavendish experiment, pretty clever. Well done, Cavendish. And we'll have to see more people access these videos and get to learn from them. Thanks again. Bye-bye.
Relativity, the explanation for gravity is that matter bends space. And so you put mass in a place in space, it warps space-time, and objects are not feeling a force of gravity, they're just following the natural curvature. And so this is a sheet of Lycra. Where do you get this? This is my old bike shorts. No, there's literally a spandex.com. You can get a sheet like this if you buy the sale stuff, so you don't care what it looks like, right? For like 20 bucks, maybe less, depending on the sale. And so you put matter, and it warps space-time. And so if I have another object, it also warps space-time. They feel that, and they're attracted to each other. And so that's Einstein's picture of gravity. Objects warp space-time, feel that curvature, and move accordingly. And if you have more mass,
you're right there on that.
If you have more mass, it's going to bend space-time more. And so if you have objects there, they are going to respond to that, right? And so you put something there, now it's attracted. Now, in reality, that big mass would feel the warping of space-time by the marble, too, right? It would move a little bit, but we usually ignore that. You know, the Earth makes the sun move a little bit, but it's so small you can ignore it. The moon makes the Earth kind of wobble around a point 3/4 of the way from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse, for a while anyway. And some more here. So one of the things I thought of to do with this is when you study the solar system, all the planets are going around the sun the same way. Why is that? Did God decide that he only liked clockwise, or depends on whether he's above or below the solar system, right? Why is everything going in the same direction? Well, the answer is it wasn't. Different directions. But there was a preferred direction. The disk it formed from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way. That works 90% of the time.
Is it like a toilet flushing? Southern Hemisphere? Wow, can you do that again?
And so, it won't work then. And so I have slightly more in one hand than another, but I don't consciously do that. And you want to get them so they spread out a little when you throw it.
It's because they're colliding with each other that you...
The ones going the wrong way get eliminated, right? Now there also would have been, this is where this analogy breaks down. There's, another dimension, right? But those things that were out of the plane also, that weren't near the preferred plane, also got eliminated. And so that's kind of cool. Now my students use a PHET simulation called My Solar System. And so they've seen all this on the computer, and when we do this during our special relativity unit, they're like, hey, it's just like the computer. That's kind of cool that a stretched sheet of Lycra models things, it's not just like it, but similar to the computer. Now, some things we've discovered using this. Also, that's just some larger marbles. You might as well put them out. But they bend space-time too, right? And so maybe, oops, you can get one thing to orbit another. I think I can do a little better. There we go.
Oh my God.
So the Earth-Moon system, maybe? And so you can see that this seam, you can't buy Lycra this big. You get it in rolls, and you have to sew it together. I've been told to use stretchy thread to sew it together. And so next time I do it, I'll do that because it pulls. And so just a little bit of thread fixes it. And so in the morning, when I first set this up, I'll have it leaning against the table. I'll be underneath fixing holes from last year. One time my principal walked in. And I hear somebody in the room, and I'm underneath. I'm in the middle of sewing it. I'm not going to pause yet. And then he's looking around for me, and he kind of knows somebody's in the room. He says, "Oh, there you are." He goes, "What are you doing there?" And I go, "I'm repairing a rip in the fabric of space-time. What do you think I'm doing?" How often do you get to say that? Another thing this does, you've probably seen plastic ones of these, right? The Discovery Center, Children's Discovery Museum in San Jose has one. The Exploratorium has one. Sometimes they have them at shopping malls to get you to put money in it. But one thing you can't do with those is put two masses in. And so when we went to the moon, when we first started, we sent our spaceships on what are called free return trajectories. So they would go to the moon. This is hard to get to happen. And they would come back in like a figure eight. And so that lets you show, now of course the moon's a lot smaller, but if you look at the plots of the free return trajectory back from the Apollo program, you'll see it has a figure eight sort of shape. And so this takes a little bit of practice to be able to do the figure eight. These clamps around here, you can adjust it to make it tighter if it's not working. So Steve and I, when we set this up in the morning, we played around with it, and actually I think it was working better than it usually is. And so not easy to do. And so I go through that. One year a kid who read some stuff about the dark energy. We have our dark energy pole.
It's over there.
I happen to have an extra pole. I guess any of these would work. And so I'm just thinking, oh, dark energy, what is that? That makes everything come apart, right? And so dark energy would be that. And so stuff goes apart rather than toward it. So if you can work in dark energy anytime, right? And so I go through that spiel. Maybe it takes me 10, 15 minutes talking with the kids, just stuff they're not familiar with. And then I just let them play. And so that's where we discovered the Earth-Moon thing. Is I just let them play, and they're like, "Mr. Burns, come over here and look." And they were all excited because they discovered that. I said, "Oh yeah, it's got it." And so there's, then I throw out a few other things so they can try this collected stuff over time. And put out all the marbles. So if you want to try it out, but we probably want to get back to electricity and magnetism.
But we want to play, Mr. Burns.
So I'd say the whole thing, if you bought all the parts and everything, it's about $100. But one of my favorite days, so you're going to do it Monday, right, Steve? You didn't get to it. But just do it once and you'll be hooked. And it will take a little bit of fooling to put it together, but I'll post the plans, and it's not a whole lot of work for.
So this is a take-apartable thing, right?
It comes apart, all the PVC pipe, wrap it with a bungee cord, stuff the Lycra in that box, and I can carry the whole thing myself. This is about the right size. You can get your whole class around it pretty much. Smaller. One problem is reaching. Trouble with that, so you get a student to do it right. One thing you got to watch though is some students will think to go underneath to push up, and then while they're underneath, somebody decides to put the big mass down, and they get their space-time warped. And so you just tell them you can't go under. We will get things ourselves. We don't need to do that.
Even Einstein has rules.
And so, is general relativity in the state standards? No. Probably the crowning achievement of science, not in the state standards. Can you fit it in after the STAR test? You bet. You can find some videos. I show them a thing on gravity waves, and then we do this, and that's, a day, almost a day on general relativity. But since I don't understand it myself, that's plenty. So let's go back into the room.
I am here at the University of Sydney, where the mechanical engineering shop has built this incredible piece of apparatus for me. It is a 40-pound, that is 19-kilogram flywheel on the end of a meter-long shaft. Can you imagine trying to hold this out horizontally with just one hand at this end? It is impossible, okay? Now I'm gonna let go. You gonna be able to hold this at all?
I've saw it.
Can you lift it out? Make it horizontal, hold it. Come on, just try to, I want you to hold it out horizontal. See if you can. Hold it. Oh, come on. No. What I'm gonna do is I'm going to spin this up to a few thousand RPM, and then I'm going to attempt just that, to hold it from one end and have it out horizontally. Five, four, three, two, one, boom. I'm going to let go with my left hand. What you'll see is that the shaft remains horizontal. You can see it going around there.
It almost looks as though the wheel is weightless. How does this work? Well, instead of pulling the wheel down to the ground as you'd expect, the weight of the wheel creates a torque which pushes it around in a circle. You may recognize this as gyroscopic precession. For a more detailed explanation, click the annotation or the link in the description to see my video on the topic. Here, I want to try something more extreme.
I'm going to try to lift it over my head with one hand while it's spinning. Wish me luck.
But before I make the attempt, Rod wisely suggests that I first check if I can lift the wheel above my head without it spinning.
Let's prove that I can lift it just this end without it spinning. Here we go. It's just kind of awkward with the hand.
Careful. Careful.
Woo! Just barely. Oh, goodness. Do you even lift? Clearly I do not.
Undaunted by my lack of strength, I'm going for it. But I want to make sure that the wheel is spinning as fast as possible to give me the best chance of success.
Give it 10 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go! That was perfect. Now I'm going to release my left hand, and holding only with my right hand at the end of the shaft, I'll try to lift it up over my head. This is a 40-pound, 19-kilogram flywheel. Ready? Here we go. 3, 2, 1. Beautiful. Let's go again. In 3, 2, 1. Nice.
Smooth.
3, 2, 1. It feels incredibly light as I do that.
When you said it felt incredibly light,
Yeah.
when you're lifting it feels light,
Yeah,
shouldn't.
I know. Honestly, I have lifted it up with one hand when it's not spinning,
Yeah,
and it feels really hard to lift it up, like it's a big effort.
yeah.
But with this, when it's spinning, it honestly felt like it was just,
Wanting to go up by itself.
yes. It felt like I was not struggling, like I was not putting in the amount of force that you'd think to lift that kind of weight?
I bet if you let it go, it'd crash down to the ground. That's not weightless.
We can't do that, though. We can't do that part of the experiment. What we could maybe do is I could stand on a scale and we could see what the weight of me plus that apparatus does while I'm lifting it up over my head. See if I get lighter, in essence. You can see that just my weight is about 72 kilograms. Now when I pick up the flywheel, it goes up to about 91 kilograms, which makes sense because the flywheel itself is about 19 kilos. That's 42 pounds. Now we're going to spin it up, and I want you to make a prediction. As I'm lifting it over my head, do you think the scale reading will be more, less than, or equal to 91 kilograms? What do you think? Standing on the scale, the wheel is spinning, and it still weighs 91 kilograms. You've made your prediction. Let's see what happens when I throw it up over my head. In 3, 2, 1. What do you think?
I don't know about you, but to me it looked like a shaky mess. Let's watch that again in slow-mo and I will graph the scale readings. As you can see, during the lift, the scale oscillates around 91 kilograms, the same as it read when I was stationary, so it seems the apparatus doesn't get heavier or lighter when it is lifted while spinning. The only large deviation from the average comes at the end of the lift, when I let the wheel fall so the scale reading drops, and then I slow its descent and so the scale reading rises. So the question remains, if the wheel doesn't get lighter, why does it feel lighter? This demonstration was first performed by Professor Eric Laithwaite. Listen to how he describes it.
So here goes 40 pounds of wheel as light as a feather. This is not a conjuring trick, this is a fact of science.
He sure makes it look easy, doesn't he?
Watch it again carefully. A fact about a spinning wheel that so far everyone has missed.
Professor Laithwaite claimed the gyroscope's properties couldn't be fully explained by Newton's laws of motion. I disagree. But in order to understand why the wheel feels so light, we first have to consider why it feels heavy when it's not spinning.
So two-handed, that's as far down the shaft as you can hold it?
Yep. Holding the shaft horizontally, you clearly need to provide an upward force equal to the downward weight of the wheel. But this is not enough, because with only these two forces, there would be a net torque causing the apparatus to rotate. So you need to create a counter torque in addition to supporting the weight of the wheel. This requires pushing down with one hand and pulling up with the other. And the upward force must be greater than the downward force by an amount equal to the weight of the wheel. So the force on each of your hands is significantly greater than the weight of the wheel. Now once the wheel is spinning, the torque due to its weight now causes it to precess rather than fall to the ground. Therefore no counter torque is necessary. You only need to supply an upward force equal to the wheel's weight, so it feels lighter. Now the trick to lifting the wheel over your head is to push it forwards as you release it. Laithwaite knew this. If you force a gyroscope to precess faster, it lifts up.
Hurry the precession and it rises.
But the weight doesn't change.
Similarly, if you slow the precession of a gyroscope, it goes down.
Slow the precession and it falls dramatically.
I'll show it to you, Rod.
Now show it to me.
It's hard to go back the way that it doesn't want to precess.
With 2 hands. So you can't say it becomes as light as a feather when it's rising.
It certainly doesn't become as light as a feather. I can say that too from having felt it. But it does feel lighter. And I think maybe part of that has to do with the fact that I'm not having to counter the torque with my hand. You know, all I have to do is support the weight of the disc, but I don't need to provide any torque with my hand to counter that gravitational torque,
Yeah,
which is what makes it feel so awkward when you're trying to hold it when it's static.
When you apply a torque, as you were, then there's a force up on one side of the hand and down on the other side. And if you decrease the force on both sides, then it will actually feel lighter.
It feels lighter without actually getting lighter.
Yeah, yeah. What it does is to decrease the apparent weight that you're feeling.
Put it on, let's see what it does.
Through this coil of thick wire, we're about to pass a huge alternating electric current. On top is a 1 kilogram aluminium plate.
So we hear this noise. What's that noise?
It's the vibration of the plate because it's vibrating at 2 times the frequency of this one.
Whoa! Whoa! How does it do that?
To find out, I've come to the place where it all started, the Royal Institution in London.
This is the key to Faraday's magnetic lab. It's amazing that lock still works.
From the 1870s onwards, it became a storeroom, which is why it survived, and it survived intact, all the joinery, giant electromagnet, exactly the same as Faraday
So this is exactly as Faraday would have had.
That's right, yep.
In Faraday's time, it was known that electric current creates a magnetic field, but it remained an open question whether the reverse is possible, if a magnetic field could generate electric current. Faraday answered this question with his most famous apparatus.
Faraday's electromagnetic induction ring, which is this.
In August 1831, Faraday wrapped 2 coils of insulated wire around this iron ring.
But in 1831, you could not go down to your local electrical hardware shop and ask for X hundred meters of insulated wire. You had to insulate the wire as you went, and so as you pushed and pulled the wire out of the ring, you had to insulate it. It takes 10 working days, which is a huge investment of time.
But the investment paid off. When Faraday connected a battery to one of the coils, he saw a brief pulse of current in the other coil. And when he disconnected the battery, he saw a pulse of current in the other direction. He realized that current was induced in the second coil only when the magnetic field through it was changing. And if they hadn't been wrapped on the same ring, Faraday may have noticed that the 2 coils repel each other when the current is induced, and that's due to the interaction of their magnetic fields. Which brings us back to this. Through the bottom coil we are passing a huge electric current, 800 amps, which alternates in direction 900 times per second. This ensures there will always be a changing magnetic field above the coil. Instead of a second coil, we're using the aluminium plate, but the principle is the same. The changing magnetic field induces currents in the plate that create an opposing magnetic field, so it levitates.
How awesome is that?
This current is not only good for levitating the plate, it can also make light bulbs glow.
A gift.
Oh, thank you. Oh, that is cool.
Not too close because it will burn the arms.
Can I put it there?
Yeah.
And just as current in a toaster element heats it up, the induced current in the plate dissipates its energy as heat.
Add some water to it.
Thank you.
Yeah, to see the temperature.
Check out how hot this plate is. Oh, that is nuts. Is this your favorite demo?
It's like a flying barbecue or something.
Tell me this is not the best dinner table centerpiece. It levitates, it gives you light, and you can cook on it. And all the while, you're demonstrating Faraday's law of electromagnetic induction.
What I need to do is talk about vectors. Because a lot of things in physics are vectors. That means they have direction. So an example would be momentum and force. Those are 2 examples of some pretty common vectors. So if I have a cart moving along here, it has some momentum in that direction. And if I apply a force to it, I can change its momentum. So for example, if I push it to the right, then its momentum will increase to the right. It all makes a lot of sense. Well, there's a similar statement we could make about rotating bodies, which is that a torque increases the angular momentum of an object in the direction of that torque. So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque is force times the distance from the rotating axis. You could call it R. So torque is the force applied times the radius away from the turning axis. Now, what's the direction of that torque? Well, we actually use a right-hand rule to define this. And so what you do is you put your fingers in the direction of the radius from the turning axis and curl them in the direction of the force, and your thumb points in the direction of the torque. So the torque is actually out this way at 90 degrees to the force. The force is down that way, but the torque vector is actually pointing out this way. So the angular momentum of this wheel is being increased in that direction. So the more I apply this torque, the more I increase the angular momentum of the wheel in the direction of the torque. So I'm making this wheel have a very large angular momentum out towards the camera, out towards you. Now, before I go any further, let's have a look at this setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum round that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be a quite frictionful wheel. So check out Destin's other videos about helicopter physics, and then come check out my channel, Veritasium, where you can find more like this. Except I don't often nearly get my head cut off by a bicycle wheel. So.
And calculate the effect by using angular momentum vectors. But no matter how good you get at calculating these vectors, and no matter how many times you do those calculations, you might be left feeling that the spinning wheel demo seems totally amazing and weird, or that these vector explanations are completely unintuitive. I sure did. So I made this video to share how I intuitively understand gyroscopic precession. We're going to start out considering satellites in orbit, but don't worry, we'll be back to the bicycle wheel soon enough. If you've played Kerbal Space Program much, this will probably be even easier to understand. So here's a single satellite in a perfectly flat circular orbit. What happens if we push up here and push down here? To be more specific, we're going to push up and down on the satellite as it passes these 2 points. If you forget that the satellite is in motion and just imagine that its orbit is a giant hula hoop, you would expect the orbit to tilt like this, but that's not what actually happens. Let's think about the satellite again. As it passes this point, we push up on the satellite. Pushing up on the satellite doesn't cause it to teleport upwards and then continue moving in the same direction. It just gets sent flying in a different direction. And if you trace out the path that it takes, the orbit is tilted like this. Now keep in mind that the forces we applied on the satellite were equal and opposite, so they combine to form a twisting force around this axis. But we can clearly see that the orbit was tilted around a completely different axis. Now before we continue, make sure you're completely comfortable with this idea. Pushing up on the satellite here causes the orbit to tilt like this. Feel free to pause the video, rewind, or even go ahead and play Kerbal Space Program until you get the idea. Now let's look at the classic example of a bicycle wheel suspended from a rope. A bicycle wheel is obviously a solid piece of rubber, but I'm going to replace it with individual balls of rubber. It makes no difference to the end result, but it makes it easier to think about. Gravity is pulling down on the wheel here, and the rope is pulling up here. These forces combine to produce a twisting force, called a torque, trying to twist the wheel this way. Now this twisting force is totally equivalent to pushing right on the wheel here, and left on the wheel here. Either way, the twisting action is trying to turn the wheel clockwise. Now we shift our point of view to look at the wheel from above. Does this scene look familiar? It looks just like our orbiting satellite, except instead of just one satellite, we've got a whole bunch in the same orbit. But once again, this makes no difference. As the rubber balls get pushed up and down, they get diverted into a new path rotating like this. Now of course, I've made some simplifying assumptions here. In reality, the torque is applied via the bearings in the hub of the bicycle wheel, rather than via magic force arrows, and the force is probably spread out around the hub rather than applied at just 2 points. But once again, it turns out that none of this makes any difference to the end result. No matter how you apply torque to a rigid body, the end result only depends on the total torque applied. So I think the model I've shown is as good as any, and I hope it's nice and easy to think about intuitively.